Okay, so welcome everyone to the 6th edition of ST4. Myself, Vik, a part of this organizing committee. And the other organizers are Boishali, Somnath, and Sabyasachi. And Sevanti will join us in 2 days something. Okay, so ST4 is finally offline after 3 long years. And this year it essentially went to some crazy turn of events. I mean, till March or April, we are not sure if we'll be able to hold it offline. And that's simply because most of the institutes that we approached essentially were hesitant to host us because of the ongoing third wave. Or they simply did not reply back to us. Probably our mail went to their spam folder. So when we almost gave up for this offline mode, then one fine day, Professor Devajyoti Sharkar decided to check his spam folder, and he got back to us saying that we're ready to host, but we have to arrange for external funding. So then we again had a tough time in looking for this funding, and then Professor Ashok Shin came for the rescue. So he kindly agreed to provide the funding, and without his funding, this workshop would have been impossible. So there's one more reason to be grateful to him. And in the process of arranging for this hosting and the funding, so we are running late in time. So then Professor Devajyoti Sharkar and Manav, where's Manav? Okay, so they were just instrumental in taking care of the bureaucracies of IIT and also these local organizers. So we thank them again. And finally, thank you all for deciding to turn up in these unsure times and make this get together possible. So most of you are familiar with this, I guess, but there are probably some new faces here. So ST4 typically runs under the banner like it's by the students or for the students. So just feel free to express your questions, whatever little doubt you have. So don't hesitate, like what others will be thinking and so on. So for the question answer session, so what we have said is like first 30 minutes, you just ask whatever you have to, but then you also should let the speaker finish. So unless there are two pressing, just hold back. So there is actually a dedicated discussion session after each lecture for half an hour, where you can again just go on. So enjoy your stay here, stay safe, make this stay productive, make friends, make collaborations, and let's make this workshop a success again. So with further delay, let's call our first lecturer, Chandramouli. He's from ICTS, working with Suvrat, and he'll be delivering the first 3 lectures on this asymptotic symmetry and celestial holography. ये वाला बटन दबाना
is actually थोड़ा ढीला. No, this one.
sounds good.
Yes.
So just put it on.
Okay. Yeah. So, this.
Yeah.
Is this working? Can people hear me? Okay. Okay. Great. So thank you to the organizers for giving me this opportunity. I'll actually be delivering a set of lectures in collaboration with Arindam and Partha. I'm not sure if they're in the audience. Sorry. Oh, hi. Hi. So I think we'll all together talk about something called asymptotic symmetries and the subject of celestial holography. Okay. So my plan of the lectures is as follows. I'll first introduce what I mean by asymptotic symmetries, and why I think it's important to study it, even from a perspective which is very different from this subject. And then I'll introduce some notions of a version of celestial holography, which I hope will complement whatever the other lecturers are going to speak. So this is So the version of celestial holography that I'll talk about is known as the principle of holography of information, and I'll talk about that towards the end. Yeah. So without further ado, let me actually start giving you a brief motivation as to why I think we should study it. Oh, I should mention some references that I actually sent out a PDF before the lectures. I think all the archive numbers are there, but in case somebody wants to know a good set of references for the first part, then it's Strominger's book or notes. And for celestial holography, or at least in this part of it, there's some lecture notes by Suvrat. I think it's called Lessons from the Information Paradox. So anyway, that's roughly some set of references. Now, the first question is, what are asymptotic symmetries other than a fancy name? The idea is that you want to study symmetries in flat space-time far away from any sort of sources. So let's just say you've got some source, some object here. Then you would like to study the symmetries of space-time at this point. It can also be studied at this point in the Penrose diagram. So this thing is known as null infinity, the space-like infinity and time-like infinity. Throughout the entire talk, I'll only be concerned with symmetries at null infinity. Okay. I'll explain what I mean by symmetry soon. But the entire discussion will always focus on null infinity. There are versions of this which have been already developed for time-like infinity, but are in progress for space-like infinity. But this is because I'll only consider massless particles. Okay? In everything that I talk about, I'll only consider massless particles, and hence I'll only discuss symmetries and things at null infinity. And so like I said, we'll talk about symmetries of space-time far away from sources. Use ST for something else. Okay. Now, this is actually not a new subject. It's a very old subject which has been, I think, studied in great detail by people like Abhay Ashtekar, Gero, and others in the 1970s and 60s. But there has been a renowned interest in this subject with the work of Strominger, and that comes about because of the discoveries he made between asymptotic symmetries and something called soft theorems. Okay, in fact, there's a greater connection, which is now known as the infrared triangle. It relates three seemingly different subjects. Okay, and so Andy discovered a set of mathematical rules which allowed one to make a transformation from asymptotic symmetries to understanding soft theorems and also to memory effect. And this is known as the infrared triangle. The reason why infrared comes in the name is because all of these deal with so-called infrared effects, as I'll talk about later. And I think after his first couple of papers, everybody jumped in and trying to find more like the validity of this triangle in more general scenarios. Okay. Are there any questions up to this part of the motivation? Good.
So can you comment about this source? So this source is just some math.
It can be some mass, it can be some scattering event, anything that's going on. Okay. Yeah. So I should not use this board again, right? Or is that the rule? Yeah. Okay, fine. Now, my own interest actually in this field has arisen from this paper that Suvrat, Alok, Pushkal, and Siddharth put out once, and which develops the idea of the principle of holography of information. And the basic idea is that if you have flat space-time and only have massless excitations in it, then the idea is that all information is available at scri plus minus. Okay? This is the basic idea of principle of holography of information. I'll just use a shorthand for that and call it phi, if at all I need to use it. Now, okay, at first glance, this might seem surprising, but this in the ADS context might be more familiar to everyone. As you all know that via ADS CFT, you should be able to read all information that's present inside the bulk of ADS by only looking at a boundary theory at any particular time slice. Okay? So what this principle would state in the ADS case is that if there's any information present in the bulk of some Cauchy slice, then it's also available at its boundary. And in here, the idea is that if there's any information present in the bulk of a Cauchy slice, then it's also available at its boundary. And towards the end, I'll try and make this thing a bit more precise.
Chandramouli, so this is just an analogy, or is there some solid backing behind this?
This, the principle? Yes, there's a very solid backing.
Yeah. For instance, for the ADS case,
Yeah.
You have the ADS CFT corresponding, as you said. So there is like quite amazing set of evidences that that is the case.
Right.
So what about this?
I'll actually give you a proof that if I have any kind of a state psi in here, then by only restricting to using observables at scri plus minus or operators at scri plus minus, I'll be completely able to recover what psi is. Okay. Any other question? And this, by the way, is only for massless particles. There's a new version which these people are trying to develop for massive particles as well, but I'm not familiar with that story. Any other questions?
So this is like asymptotic ADS. I mean, this is flat space.
This flat space time. In a sense, so I'll not tell you what the boundary theory is. What I'll tell you is where the boundary theory should be present.
Okay, just that I. So why? So this I plus minus is the space like infinity, or is
It's close to space like infinity, but like there's the thing is if you keep going in this direction at in flat space time, then what you observe is you roughly observe some sort of de Sitter space with the top portion being scri plus minus, the bottom portion being scri minus plus, and this full thing being equal to what you call space like infinity. So in a sense, it's the past of future null infinity. Scri plus minus is also known as the past of future null. I could have made a statement also about scri minus plus, but the story is exactly analogous.
okay?
So
No, what do you mean? So this is supposed to have all
Yeah, but you know, any information that goes out from here, from scry minus, it ends up at scry plus. Any information about massless particles. So in a sense, whatever information is already, whatever information is contained here would also be contained here.
But then, so I minus plus is also supposed to have some information.
I minus plus. I could have also made the statement at I minus plus. That's right.
That direction.
What do you mean that direction?
So you,
This is scry minus plus.
okay, I guess we'll talk about it later.
Yeah. Okay. Any other questions about this?
Yeah, just one speculation. For the data for the massive
Yeah.
case, so where will the information be?
So one might naively think that it should be at I plus, but actually what these people are trying to do is they are now trying to develop a formalism by which you can recover it at I0. So the data about massless and massive particles together should be present somewhere in this region, like an intersection of scry plus minus and a part of I0. Okay. Okay, anyway, so this is how I got interested in the field, because Suvrat comes and asked me one day to try and understand how this would work in higher dimensions. And what we learned then was, in higher dimensional spacetimes, you didn't have a good understanding of how the phase space worked, which basically took us back to understanding how asymptotic symmetries worked in higher dimensional spacetimes. But in today's talk, or even tomorrow's thing, I'll not talk about higher dimensions at all. I'll mention some cases in which it's easier to study higher dimensions, but other than that, I'll not talk about this. So this thing, for black holes, the idea is that you assume that black holes would evaporate. Once it evaporates, you just have a collection of particles again. So we do not completely understand how it works in the case of black holes. There are some speculations that, yes, it should still hold, but it's not been proven yet. So the argument which we give is you just assume that the black hole evaporates and it should just work. But yeah. Okay, great. So if there are no further questions on the motivation, I'll actually talk about the chunk of the lecture. Okay. So like I said, the things that I'll be interested in would be symmetries at null infinity. I'll explain what I mean by symmetries and which transformations I'm talking about. So okay, for a large part of the talk now, I'll have nothing to do with this picture. So you can just completely forget about this picture. I'll only talk about the first part, which is asymptotic symmetries. So for studying null infinity, it's found that you can work in a convenient gauge choice. And the convenient gauge for working at near null infinity is known as the Bondi gauge. And by the way, everything that I'll talk about in this talk would always be at scry plus. But there's a completely analogous story at scry minus, with just some u's replaced by v's and so on. So I'll not give you the formulas for those. Yeah, like I was saying, the gauge choice which is convenient for studying symmetries at null infinity is the Bondi gauge. And you recast the metric in this manner. It might look complicated at first, but it's just a convenient parameterization which makes other formulas look very simple. Okay. So u in here is the retarded time. It's just t minus r. And r would be your distance on the sphere, like it's basically x1 square plus x2 3 square. And the first thing you would like to notice in this gauge is that a few of the metric components are just 0. Okay? Specifically, you've got the RR component, the RA component set to 0 all the time. This is a part of the gauge choice. And there's another condition which comes in, which fixes the determinant of the metric, GAB. Okay, so GAB is the metric on the sphere. These ZAs are the coordinates of the sphere. So if you're in d plus 2 dimensions, then these z basically runs over theta and phi in 4 dimensions. Sorry, if you're in d equal to 2, then z would basically run over theta and phi. Okay. Okay. So there's another gauge condition along with these guys, which fixes the determinant of this. There are many ways of writing this determinant. One convenient way of writing it is this. I should give a disclaimer, this is not a unique choice. This is just one set of conditions, which we'll see what it does later. But you could have relaxed this condition and instead fixed beta to be a particular value. This has a name, it's called the Neumann-Unti gauge, but the names are not that important. Now, what I want to do now is to say that I'll tell what UAs are. For now, it's just a function of small u, r, and z. It's any function of that. So are these m's, beta, and u.
Capital U and small u are different, right?
Yeah, they are different. They're looking same. So this is capital U. Small u is the retarded time. I'll just say why it's related to the flat space metric.
U is only t minus r as you go close to infinity, right?
Correct.
The bulk, it could be something else.
Yeah, this is. I'm going to just talk about the follow-up conditions. Yeah. So the thing is, I would want this metric to be true in as he pointed out as we go to scribe plus, and what we would actually want is that the metric at exactly r equal to infinity. I'm not sure how to say it, but something of this sort should be the usual flat space metric. So this guy is basically our d theta square plus. Okay, this is a usual flat space metric, and we would want this these guys to eventually reduce to this if you're strictly at null infinity or something. Okay, if you're like completely far away. So what this means is that this allows us to fix what are called fall-off conditions on each of these metric components. Okay, by fall-off conditions I mean that. Oh, good. Oh, shit. There's no way in which I can make this board not hidden and still use it, right?
Erase that board and bring it back.
Yeah, good. That's a good point. Is it all visible? Okay, great. Huh? Yeah, I'll just be using this expansion, so.
After m or e to the power in front of e to the power 2 beta.
Yeah, it's m. It's going to be related to something called the Hamiltonian. I'll come soon to that, yeah. Okay. So let this be here. So this is the general metric in the Bondi gauge, and like I said, we want this to reduce to the usual metric that we all know of as you strictly take r to infinity. Okay. What this means is that these guys have some fall-off conditions with r, with small r, and they look like this. So we allow for very liberal fall-off conditions. These are valid whenever you have massless particles, and they just look somewhat like this. GAB in particular is going to be important for us, and I'll write few components of the metric explicitly. Okay, so these are what are called fall-off conditions. Now, these are not the most general fall-off conditions.
So,
Yep, right.
what is capital omega? The angular part.
Yeah, so omega is, thank you, omega is basically theta phi. Okay.
So why did you start with such a metric? I mean, like,
So the thing is, you could, like, you know, in 4 dimensions, you could fix 4 components or 4 coordinates easily, and these are the 4 coordinates that I'm fixing.
like for example, GEU has this typical.
These kind of things, I could have parameterized them in different ways. This particularly will shed light on why it's, I'll talk later about why it's important to write it this way. What we'll see later is one component of M would reduce to what's called the Bondi mass, by which you can compute the Hamiltonian of the theory. Okay? Any other questions?
This last gauge choice, that scalar of negative
Huh.
equal to 0, is that valid only at the boundary, or is it throughout all the spaces?
I mean, this particular, this whole thing, as you see, we're going to assume there's a series expansion which follows. And as you go very close to where sources are, we do not know what's going to happen there. So for us, everything will be true asymptotically. So this condition, what it will help is, it will help in fixing the traces of these guys. Okay, that's all this condition would do. In fact, I could have never talked about this condition and instead fixed any one other particular component. One thing was like fixing beta, for example. You could have fixed beta to be some particular value and relaxed this condition.
This metric is a solution of the vacuum Einstein equation?
This full metric, it would solve the vacuum Einstein equation.
Maybe I can add a couple, like this, the metric that you have written,
Yeah.
it can in principle solve even per de Sitter and ADS, right? I mean, later on you impose these fall-off conditions that ensures that it's only
And only flats. Okay, this I'm not 100%. Maybe you're right, but this I do not. I'm not sure.
One more motivation for
Yeah.
the gauge condition. So the determinant condition, like you said, you have lesser variations, but the GRR and the GRA equal to 0. You can think of it like what you want is you want to look at things at null infinity.
Right.
So you want some sort of a null coordinate.
Ah,
So
yeah,
the only way to
right.
define, like, so you define a U coordinate such that the normal to this surface is always null. So
Right,
that fixes
right.
these two conditions.
Right.
I mean, the GRR equal to 0 condition, and the GRA is you want the transverse direction to the null surface to be spheres. That fixes the GRA to be 0.
Right.
And this is an additional condition which I don't have a good motivation for.
Yeah. I mean the determinant condition, as I said, is not. This is not unique. You like one way to also think about what you said is like, you know, you've got four kind of epsilons which you can always transform your metric by, and these are basically your 4 choices of coordinates, like, you know, and.
So if you use this gauge condition for even de Sitter spaces, you still use this condition that GRR GRR.
Yes, so you can if you want, but then you will not impose. So besides this fall off of the M, UA, and beta,
Yeah.
I think they will be different.
Yeah, they'll be different, but I'm saying that this gauge conditions that you choose, that GRR is, because there you don't have a null infinity.
Correct. So, but if you want to do this lambda BMS, the way compared and all those, then you want to use something like this. So the main motivation for that gauge choice is you want a null coordinate U. So such that if you follow U, fix U are going to infinity, you reach the plane where radiation
Right.
is enter. So to study radiation, this is a very good gauge choice, and this is Bondi and others too. And most of the literature is on this gauge choice, so we just follow the.
Right. Yeah. Indeed. Yeah. Okay. Thank you. Yeah.
Why did you say this is not the most general?
Sorry. The most general fall-off conditions. Yeah. So I was just coming to that. So these fall-off conditions are valid when you have massless particles. Suppose you had massless and massive particles in your system, then along with these, what you'd find that you'd have to add logarithmic terms in all of these fall-off conditions. Log terms are dimension dependent, indeed. One way to see it, I'm not sure if I should talk about it, but one way to see it is also from the soft theorem side, that there are certain new soft theorems which have log terms, specifically in d equal to 4. And I think there's this paper by Kapon which has analyzed these log terms and general dimensions. But yeah, they are dimension dependent.
One more question is, if you look at the signature of the metric, the du square term,
Yeah.
first metric is like always positive.
Oh no, m0 is actually going to be -1 for us.
There should be an equation connecting m0, u0 and
There will be. I'm coming to that. Yeah. So not all of it in this metric is free data. Okay. Thank you. In fact, that's probably. No, you would need to include log terms if you have massive particles in your system. You'd have to assume for fall-off conditions, which like log r by r part m or something, when you have massive particles. But turns out that when you have massless particles, you can just set these to 0 and nothing ever gets affected.
Even for this massless case, does this work for both Sky Plus and
So this particular way I've written down, it is specifically to Scribe Plus. I could have written down an exactly same metric with u replaced by v, the advanced time coordinates, and wrote it as Scribe minus. Okay.
the series extension, 1 over series extension, they work for even when you take V, they work for the Sky.
Yeah, exactly.
Both cannot be represented at the same.
They can be. There is, I'm forgetting the name of that, but there's a particular coordinate system where you allow r, the small r in here, to go from -infinity to +infinity instead of 0 to infinity. In the way I have written down, it goes from 0 to infinity. But if you would have allowed for small r to go from -infinity to infinity and made a slight replacement in all of these coordinates, I don't recollect what, but then I think the r equal to infinity limit gives you Scribe plus, and r equal to -infinity would give you Scribe minus.
What is X?
Oh, x, these are like your usual 3D, like x, y, and z, or whatever you'd call it, from the origin. I'll not use that at all. That's not be used.
Metric, there is no X.
This is not important. This is basically the radial distance from the origin or something. That's all it is.
So in your metric, there is no information that you have any horizon or anything.
Any horizon or anything. So in this particular
You are just considering just to try to find out a metric which is convenient for.
Scribe plus alone, yeah. If you had a horizon, then you would have to also write down something else at the horizon. In this case, I'm assuming there are no horizons.
There is no horizon.
Yeah, in the way I've written down, I'm assuming there are no horizons. That's right.
So if anyone wants to.
You could do that. You could also add horizons and do all of this. Then basically you would have to take care of things at both the null boundaries. You'd have to take care of stuff here and here at the same time. That can be done, but
Some additional follow constant on the horizon.
yeah, you have to put some additional follow conditions.
In that case, would it be possible to do these gauges?
When you have horizons and stuff, I think this gauge choice is pretty general. Like Anish was explaining, it's just got to do with null infinity. The last one is see, the thing is, in general, you can always transform g mu nu by a set of diffeomorphisms and choose 4 vectors to bring it to whatever form you want. So that's like fixing 4 of your coordinates. So these things fix 3 coordinates for you. Like A is running over theta and phi, so it's 3 choices. And this is the fourth choice. You could have also chosen something like beta equal to 0. You could have also traded this for something like beta equal to 0, for example. That's another choice you could have also done. It's just convenient to do this because, I don't know, most of the results you want to look up to have already chosen this. Okay.
Just one live question would be, so the thing is, you said that for the massive case, you'll have to include log
Yeah.
terms, right? Now, you're doing things near Scribe plus, right? And the massive particles will never go there. Right?
Correct.
So it's like they will, this particular surface will never see their presence. It appears like that.
It appears like that, but I think what happens is, as I'll just say now, the equations of motion which connect various components also somehow connect some information about that to all of these. And if you don't include them, then you run into some inconsistency.
So that means, okay, from looking at the symmetries there, you will be able to know whether there are some massive particles present in some.
By looking at, I'm not sure if that's a correct way to put this sentence, but okay, I do not have a better way to put it right now. So all I can say is if you do not put that, you'll run into some inconsistency. But I'm not sure if you can transform it to the level of the charges of those symmetries or something.
So what I meant to say is that if there are no log terms,
Yeah.
that means certainly you are dealing with massless particles.
I'm certainly dealing with massless particles.
If there are there,
Then you'll have to, then it indicates a signature of some massive particle in a sense.
certainly.
Certainly, yeah. Because I mean, okay, if you think of the world as just massless and massive, then massless alone does not require them. Okay. Great. Are there any other questions? Or? Okay. So yeah, the reason for parametrizing this in some weird way like this is, as we'll see this, that some particular component of Mn will be related to what I call the Bondi mass aspect. And integrating this would give you the Hamiltonian. Similarly, a particular component of this will give you the angular momentum aspect, which will, as the name suggests, give you the angular momentum. And these guys parameterize the radiation. In 4D. Okay, so any kind of radiative data that you would have would be parameterized by this particular tensor CAB. Okay, and this is a dimension-dependent statement. If I were in higher dimensions, then I'd find that the next component of this series expansion would parameterize the radiation. Okay. Should also mention that all these A, B, and these indices that I write down, A, B, and so on, they are all raised and lowered by gamma AB. Okay, so in a sense, UAN is equal to gamma AB UPN, and one can actually just prove it by assuming that the full indices are lowered and raised using G mu nu, which is what you would expect. Okay. Okay. And also the determinant condition that you have, this guy, it fixes the traces of all of these, and in particular for CAB, it tells you that it's traceless. Okay. Yeah.
Did you say anything about beta? What information?
Yeah, I do not actually know. That's the honest answer. I do not know what information beta has. Yeah. If anybody else knows what information beta has, just fill it up. But I do not know the answer. It, like for example, one answer could be that this trace condition, for example, fixes. The determinant condition, for example, fixes the trace of this. It can be proved by using the usual relation between determinant and traces. So maybe I should leave that as an exercise. Prove this. And this tells you that there are basically two independent CABs which exist. Since it's a symmetric tensor in 2 dimensions, and one component is set to 0, so you've just basically got 2 independent tensors, which later would turn out to be the 2 independent polarization vectors for the graviton. Okay, I guess if you would, you could have since you could have traded this condition for fixing some value of beta, I guess beta would have told you something like that then. But other than that, I do not know anything else. But anyway, okay.
Is there any reason why that expansion starts at R1 over R, not 1 over R?
Good. So thank you. So if you actually strictly put R equal to infinity in this, then what I'd want to get back to is this metric, the usual flat space metric, and everything that I'll allow for will be subleading in comparison to this. Subleading in the R expansion is comparison to this. And one motivation for that is you would want your energies and other fluxes that you compute to be finite. Okay, and if you allowed for let's say, higher order terms in this, for example, n equal to -1 in this, then the terms that you would get would simply diverge.
Yeah, I was specifically asking about beta. So it starts at 1 over r.
I think beta equal to 0 would be like beta naught, which would give you a coefficient of 2 power e power 2 beta naught or something. So beta naught is just fixed to be 0 because you want this guy. So like, huh?
When you say mu is the bonding mass, and if you integrate, you get the Hamiltonian.
Sorry, that's not mu, that's m, sorry, yeah. Not this full m, but one particular component. In fact, in 4D, it's m1.
Hamiltonian is generally a constant in this theory, right? So how do you make sense of mass being a constant in the theory?
I'll come to that. I mean, I'll tell you about how the Gauss constraint actually gives you this thing in a second, yeah. Okay, are there any other questions? Okay. Good. In fact, these guys have a name. The CAB in particular has a name. It's called the shear tensor. Shear. And the derivative, the U derivative of that, del U CAB, is called the News tensor. And that's simply because if you would compute the stress tensor of the graviton or something, you'd find that it's NAB, NAB, which it just carries the news about the radiation. That's some naming thing. Okay, so now what we would like to do is we would like to study the symmetries or the particular set of transformations which retain the form of the metric asymptotically. Okay, in a sense, what I'd want to do now is study the set of transformations over G mu nu, which fall off as some particular power of R, where this n is basically fixed by your gauge choice and the fact that you would want to keep this form of the metric asymptotically. Okay?
Chandramouli, what happened to that U index in used in
U index. U is not an index. It's a derivative with respect to U. So U omega, and this is a function of U and omega. It's just del U, the derivative with respect to the retarded time.
specifically is defining?
It's just a definition as of now. Okay. Okay.
And this Killing equation you were saying you want to solve it order by order.
I'll solve it order by order, and I'll also make sure that some of these conditions, for example, like the GRR and GRA, they should be respected at all orders of R. And what things which I would not want to change would be, for example, in the GUU expansion, the first term is -1. First term which you would expect would be -1. And then you would have things which fell off, which are basically a combination of M, beta, and U. Collectively, I write them as GUU 1 by R. So on. So when I put an n here, what I mean is that I'll make sure that this guy is not changed. Like till this order it's unchanged, but these guys could change under some diffeomorphism.
So at every word you will find killing vectors.
Yeah, I'll find a killing vector as a function of R, as 1 by R, whatever you want to call it. Yeah, this expansion 1 by R. Okay, so in fact I'll not solve these equations for you. Again, I can. It's a trivial exercise, and so you have to basically solve these equations for the gauge choice and for the other conditions. And what you would find, and I should mention that these are restrictive, and I'll talk about what restrictive means very soon. Yeah, one second, please. And in our case, d equal to 2. Yeah, go on.
So I'm saying that you are not taking any expansion of killing vectors around 1, right?
So in order to get this exact form, it's necessary that I'll have to take this guy as well. That I'll have to solve this order by order R. I can write down a general expansion in terms of R, but the way you should see it is that you should see it as a perturbation series and 1 by r. Okay, like a large part of this formula that I've written down in here could have been fixed from just your gauge choices, these gauge choices. Okay, just to show you one of them. So in particular, you look at the general solution for G mu nu. Okay, let's say this is the most general equation that you could have written down. And in particular, you would want the RR component of the metric to always remain fixed, to be equal to 0. And if you just substitute these coordinates, what you'd find is that del R of xi u must be 0, which tells you that xi u is actually independent of R. Okay? And by imposing further the other kind of conditions, you'll specifically find this guy to be a function of z alone, which is the f of z that I've written down. Okay, I'll leave it as an exercise to work out the rest of them.
Can you tell what is the role of n here? I don't see n on that side.
You don't see n on which side? Oh, okay, good. So n in a sense, okay. So some of these conditions are valid for all R. Like independent, like for example, this condition. This is the gauge choice which I'd wanted. Similarly, I would have to impose this. Okay. We'll see that these conditions, along with the determinant condition, would fix a large part of this, but not get you this form completely. However, what you'd want is, say specifically you take one particular component of the metric, like GUU, and you take the, like this is the expansion that you would expect for GUU, right? And I'm saying by this n here, I mean that I would not want this guy to change. So that's all. So for example, if I write down delta xi GUU, then this can change up to order r per minus 1.
Okay. So for each n, you got this equation.
Each n I do what to the equation?
So for each n,
Yeah.
you can write this equation. Is that what you're doing?
No. All I'm saying is that depending on the particular metric component you have, depending on what these mu nu's are, for example, if mu nu was equal to RR, then n is just like, doesn't, like you should not put anything here. It's valid to all orders in R. You gauge choice. Similarly for the RA component.
So n is not that index that's going to be summed over.
Oh, no. N is basically telling you how this thing falls off.
Okay.
Like for example, for the UU component, n is minus 1. For the,
Is this something which can vary?
exactly, it's just something which can vary depending on which index you choose. This is just a shorthand way of writing it.
Fine.
Okay.
You fixed the metric on this here? Like
Yeah, I'm going to fix the metric on this period to be the.
it is fixed, right?
It's fixed. It's correct. So that yeah, I'll just comment on that point. But yeah, other points. Yeah. Any other question?
While you were using, you were considering null infinity.
Where am I using null infinity? All of this is true at r tends to infinity, and r tends to infinity is null. Yeah. Oh, this. Oh, okay. Thank you. So this d is the covariant derivative on gamma ab. I should have mentioned that. These are. Which is.
The expression for epsilon a, why are you not using gamma ab to raise the index?
No, this is the exact form of the expression, the way you would have, like for example, this GAB has an expansion in R again. So the inverse of this metric is defined with this condition. GAB, GBC is delta AC. So you'll have to compute what the inverse GAB is.
Gamma b is the limit r tends to infinity.
Yeah, gamma AB is your metric on the sphere, the usual metric on the sphere. Yeah.
So to raise and lower, you use GAB and not gamma ab.
No. This I'm not raising and lowering using anything. This is just the general expansion. For example, this GAB that I've written here. Okay, this guy is gamma AB by 2. Gamma AB by R square minus CAB by R cube plus CAC CB minus the next component of this expansion. If it's DAB, then it's dA b by r power 4 and so on. And all these AB individually are raised and lowered using gamma. So for example, if I would have written down, say in this particular case, if you have dB of f, and then you've got GAB, like this guy, then the first term in here would become dAf. Okay, and the next term is simply your dBf times CAB by r cube. Does that make sense, or should I say it again?
Epsilon also has an upper index.
Yeah. Yeah, so the full epsilon, for example, is basically epsilon u del u plus epsilon a del a plus epsilon r del r. So okay, let me say it this way. In a sense, what you should do is you should think of this epsilon as summation over n epsilon a n by r power n, and all these guys are raised and lowered using gamma AB. Does that make sense?
So this is the equation del xi g mu equal to 0. You want to solve xi.
Yeah.
Then you assume a expansion for xi.
You can prove that there's a closed form expression which looks like this, but in a
u del u plus xi del
where these xi u's are this, xi a is this, and xi r is this.
Then these xi u xi a these also have expansions in R
These are all actually expansions in R.
because they are function of R.
These are all functions of R which are polynomial, or I'm not sure how to call it, but it's expanded in 1 by R. The series expanded in 1 by R. And these xi a's in particular, once you've series expanded them in 1 by R, then they're just functions of u and omega, and now their indices can be raised and lowered using gamma AB. That's all I'm saying.
So in the expression for epsilon a, why don't you have a GAU term?
Why don't I have a GAU term? So I mean, this is just an expansion which solves this equation. There's just I'm writing the solution for you. I can prove this, but like I'm saying, like for example, the way you would prove it is you start with any particular component of the metric, write down this equation and plug in the components. And for example, for this particular component, you will be able to show that xi u should be a function of u and z. By using further restrictive conditions or the other components, this guy would solely reduce to a function of z, which is what I'm calling f of z here.
Actually, you're imposing a condition that Lorentz transformations are not part of this.
Yeah, I'm coming to that. It's related to the question he asked because.
No, I'm just saying that if you solve the killing equation exactly, Lorentz transformation should also be present.
Correct. Here, in this case, I'm assuming that the metric on the sphere doesn't change. So.
I'm saying Lorentz transformation.
Yeah. That will be related to that.
Okay.
Like if you allow your metrics on the sphere to change, or you're just saying, just Lorentz. Yeah, correct. Just boost, for example.
So that will have a u-dependent term in the xi u component, right? It will be f plus u by 2 dA by a, where y is just the Lorentz transform.
True. In this,
Should have a,
yeah, in the most general solution, including them, will also have that. Correct. You're right. Yeah.
Yeah, so it's an asymptotic expansion, but the question he asked where is exactly this null infinity here. So u is the null coordinate here, right? So,
U is the null coordinate and R is the affine parameter of that. Yeah.
so can you formulate something like large u expansion?
Large U expansion, I'm not sure if it's a good idea.
Keeping u fixed is that,
Yeah.
keeping u fixed, if you take r,
R goes to infinity, it's.
but then how do we reach this I0?
In this case, I'm not going to reach R0. Yeah. So in this entire thing, I'll never talk about I0. I'll talk about scribe plus minus, which is you first go to null infinity and then take u goes to minus infinity. That will take you to scribe plus minus. Okay. Okay. Sorry, how am I doing on time or something? Is there a clock?
Yeah.
Oh, okay. Okay, so it's 1 hour. Okay.
This xi will include Lorentz transformation.
Yeah, so
Exclude and
how to?
exclude Lorentz transformation, and if you solve for general xi, then
if you, so again, that would eventually come down to also studying transformations of gamma AB with other components. Like in this case, for these particular set of metrics, it just excludes it. But if you,
So this is a particular solution that
there's a particular solution which excludes that. You're right. But I could have chosen a more general class of solutions, and it's just more convenient to talk about all of them together in what are called super rotations. I'll come to what super rotations are.
You're saying if you're keeping gamma AB fixed,
Yeah.
you're excluding Lorentz transformation.
If I'm keeping gamma AB fixed and also some other component of the metric fixed,
And you're keeping Lorentz transformation.
I'm excluding Lorentz transformation.
Lorentz transformation is part of Poincare, right? So this Minkowski, this metric that you've written minus du
Yeah,
square
yeah.
plus 2 du dr, and gamma AB even with fixed, it should still have a Poincare symmetry. So there should still be Lorentz algebra, right? Doesn't have to do with fixing gamma AB.
No, you're right. I mean, in order to take the full Poincare algebra, like including translations and boosts, and boost. So this thing, what I'm doing now is just talking about a generalization of translations. I'm switching off boosts, in a sense. But had I taken boosts, and I would have allowed for transformations on both gamma AB and some other component of the metric, and like a more general solution of Xi would take care of Lorentz transformations as well.
So you're just looking at the
Subset of that, some subset
super
which,
translation, just the
exactly. I'm just looking at super translations.
Okay, first you're doing
I'm just taking super translations.
So the precise condition would be that on Xi,
Yeah.
if you say that it doesn't have an order R piece because
Correct.
Lorentz transformation goes as order R.
Order R.
If you don't have an order R piece, then you get only super transformation.
Exactly.
So if it's exactly 0, then you get everything. Is it?
Sorry, say that again.
If it's exactly 0,
What is exactly 0?
that condition.
No, you can't solve it exactly 0,
Yeah.
right? Because that is isometry equation. Like that means that you have a particular solution of Einstein's equation, and you're looking at isometry of that space-time. But what you're looking at is you're taking space of solution, and you're looking at the symmetry of the space of solution. So from one solution, you will go to another solution. Only Poincare will be the isometry, like
Correct.
of Minkowski.
Okay, so that will give point correct.
Right.
But so how do you get Lorentz transformations then?
Um,
In this equation, so what
The
do
same
you do?
equation, but
Yeah.
he's implicitly put a condition where you, just for simplicity, to solve many of these equations, you say that Xi does not have an order R component. Lorentz transformation have an order R component. So if you solve it exactly, there will not be order R square in Xi, but it starts at order R.
That's
and
right.
Lorentz transformation have an order R component. So just to kill that off, you just say, oh, I'm only looking at order 1 and below in Xi.
You mean 1 over R or R?
Order R.
Order R, like
So n equals to -1.
n equal to -1. That's right.
In Lorentz transformation.
That's right.
Okay.
That's right. This is a restrictive choice. This does not give you the full Lorentz
By choosing
transformation.
This, so right now your n is positive, so you cannot get a Lorentz transformation.
No. So see, there are two expansions. One is the metric, right? The metric is fine.
Yeah.
I'm saying that if you, in the Xi, okay, all you're saying is that I don't have an order R in Xi. So if you naively think there is an order R, if you think of Xi also having a 1 over R.
Correct. Yeah.
If you just put the constraint, just for simplicity, just put the constraint that there is no order R piece in Xi.
Okay.
Then you get this equation. But so, like he just showed, right? He said the Xi u is actually a function of u and z, right? Where he showed this example that he showed, dou r of Xi u equal to 0. That came from the equation gauge condition.
This condition is what he's talking about.
Right? So Xi u is actually a function of u and z. But in the above, he is only written a function of z.
Function of z.
So the u dependent is actually a linear in u term, which is related to Lorentz transformation,
Correct.
and you can generalize it further.
So this is a special choice of this. So in general, the solution looks like f of z plus, I think it's u alpha of z,
Right.
where these alphas take care of your 4 vectors on the sphere. Like alpha is somewhat of dA VA by 2 or something, and these switching of these VAs is like switching off Lorentz transformations. In fact, the most general solution, which includes Lorentz transformations and super rotations, would be just replacing f with f plus u alpha. That's the most general solution that you'd have.
Okay.
Okay.
These guys, are they like closed in some algebra or so?
Good. I do not remember the answer on top of my head. I believe that in order to show that the full algebra closes or something, you have to, like, I think this was a point of debate for some years, like whether the algebra of these guys, which are known as super translations and super rotations, they actually close or not. that required some work. I believe in 4 dimensions it's sort of understood that they close under a particular choice of super rotations, but in general I do not know if one knows the answer to that question. Yeah. Okay, any further questions of this?
They close with some modified definition of
Yeah. In 4 dimensions, so the thing is, the original definition of super rotations was, actually maybe I should not mention. So there are 2 convenient ways of understanding these kind of transformations. One of them is known as the, like, one of the extensions of your original BMS group is known as the just naively extended BMS group, and the other one is known as the generalized BMS group. And I think in the extended BMS group there was an issue of these commutators, like if somebody remembers. Okay, it's probably in the extended one there was an issue, but in this generalized BMS group there was.
Asymptotic, these generators, they get closed, but there is issue when the charge algebra.
When the charge, right, correct.
But
Here they do get closed. Okay, great. Right. So you're saying the space-time action doesn't have a problem, but the charge algebra has a problem. Correct. Yeah.
If you write, the right hand side always has something field dependent.
Yeah.
Right.
And that's the problem.
I see. Okay. I see. Okay. Great. Thank you. Great. Okay.
So what is the answer? I mean, is Xi forms a closed algebra?
Yeah, as they said, Xi, I think, if you just work with something like delta Xi1, delta Xi2 on any particular thing, then I think these kind of things in general close the algebra that you would want to define from these. But as I'm just going to talk about now, you can also define charges corresponding to these symmetries. And if you would have translated this into the statement of charges, then that would naively not close.
So, is it Noether charge or something?
It's the Noether charge. Okay.
Algebra, you are saying that it's a Noether charge.
Correct. Is the Noether charge. That's right. Okay. So with these Xi's defined, you can actually compute the variation of these particular metric components. In particular, the important one is to study the variation of CAB. Henceforth, I'll use a notation of delta F to just denote these particular choices for Xi without the alpha. So for now, just forget about alpha, setting alpha to 0. And so what you have to do in order to compute this is you compute the variation on GAB and look at this to order R. And this thing then just gives you F times WCAB minus okay, where this is just saying it's the trace-free part of this, and by trace-free I just mean, so for example, XAB trace-free just means XAB minus half gamma AB times XAXC. Okay, so that's what trace-free means. Okay, and similarly you could have also written down the transformation for the news tensor, so on. Now with these transformations, it's actually sufficient, or it's actually possible to compute the charges corresponding to the symmetry. And the way you compute the charges is using the Noether procedure. And for that, so is there a question? Or? Oh, trace-free, this is the definition of trace-free. You just remove the trace of it from the. Okay, so in order to compute the charges, it's convenient to write down the symplectic form in this theory. This 2 is due to 2 dimensions. If you were in D dimensions, then this would be just. If you were in D plus 2 dimension, then this would have been D. Yeah. So maybe I should mention this. The trace of gamma AB is D. Okay.
Sorry, why did you write the second line?
Which second line? This guy?
Yeah.
Oh, so I'm just telling you a way in which you would compute this object.
Okay.
you would basically evaluate this thing at order r, and you would get this. Okay. Okay. So in order to compute the charge, what you can do is you can write down the symplectic form of this theory, and this turns out to be fairly simple. I'll mention later as to why this is subtle and why perhaps this is an easier reason to study, or why perhaps it's easier to study this in higher dimensions. Okay. So this thing is basically a way of writing down delta Q wedge delta P. Okay. And what this does is it defines your Poisson brackets in the theory. So for example, if you just had free particles or something, then this thing would have just reduced to Qi delta Pi with a summation of I going from 1 to the total number of particles. We can talk about the derivation of this. I'm wondering if I should do that now, or there's some discussion session, right? Can I? So I'll postpone the way you would derive this expression to the discussion session. Okay, but for now I'll assume that you have evaluated the symplectic form and basically evaluated your conjugate variables. So this thing is tells you what your conjugate variables are. Sorry. And using this, you can actually compute the charge of your theory, the Noether charge, which is defined using this relation. Okay, now this notation is a bit confusing. I'll explain what it means. So using the Noether prescription, you'd have basically, by once you had the symplectic form, you would have been able to compute the charge. And in the left-hand side, this delta slash means that, in general, the right-hand side need not be a total variation. Okay, I should mention this is QF. So what does the right-hand side mean? In this right-hand side, as you notice, I've got two free variations here. Like both are arbitrary free variations of whatever quantity you have in your phase space. And one of them I'll set to delta F, because I'm computing the charges corresponding to supertranslations. So I'll just set it to whatever that corresponding quantity was. And the other is left free. And if it so happens that this full thing reduces to delta of something, then you can define your charge consistently. If this full thing reduces to a total variation, then you could define your charges consistently. However, if this, sometimes what happens is this does not reduce to a term like this, but it has something else which looks like x delta y. And in those kind of things, you cannot define your charge consistently. Okay? But in this particular case, it so happens that you can define it. And so this QF, okay, let me actually just show a part of the computation. So let's say if you would have wanted to compute the right-hand side, what you would have to do is compute this guy. So I'll just use this integral as a shorthand notation for denoting this part of the measure. Okay, this is just the anti-symmetrization which comes in. And upon plugging in the values of delta F CAB and delta F NAB, what you can show is this guy reduces to this is my definition in the way I've done it. Yeah. Okay, so this is an expression that you just obtained by plugging in the variations. Just probably missing a Maybe I have not missed, okay. And now in order to, so what you see is that this full term in here, there's this first part in here, which can actually be expressed as a total variation.
So is it unique? I mean, always I can add.
You can add some sort of a boundary term and so on, yeah. Yeah. It's the same thing as the general uniqueness of no other charge. It's the same thing. Correct. Up to some other boundary term or something, yeah.
So you are not considering.
I'll not consider the most general expression. I'm just considering whatever I have here. Yeah. So, okay, in this thing, upon simplifying this, it can be reduced to a set of two terms. The first term is actually a total variation because since FAB is just a function, you can just take a total variation here. And this guy is also total variation because you've just got delta x and x, which is basically roughly something of this sort. However, this object is, I'm missing a delta somewhere. Probably it's a delta CAB, yeah. However, this object is naively not a total variation, but upon imposing sufficient fall-off conditions for NAB, this object actually goes to 0. Okay? So what I mean is that this guy's, as you see, this thing is an integral in, I mean, the integrand consists of del u, so it's a total derivative in u, and therefore it only depends on the values of CAB and NAB at scri plus plus and scri plus minus. And upon imposing that these guys fall off with small u, you can actually set this term to 0. And this fall-off condition is also going to be motivated from just the finiteness of the stress tensor of the graviton. Is this point okay, or? This, sorry, so which line am I? Oh no, this is a full, like this. So this thing is equal to this first line here, which is equal to this minus this. Okay, and the one term in this is a total variation, and the other term is a total derivative. Okay, and the total derivative term you can set to 0 by assuming NAB falls off as a particular power of u. There should be some power of u, which would play a role, but it's, in this case you would just choose some power which makes this go to 0, and that's also the power which you need to choose in order to make the stress tensor of the graviton finite.
What do you mean by stress tensor?
I'll come to what I write down, but in the stress tensor of the graviton is naively just NAB is what the stress tensor goes like. The UU component of the stress tensor. Like for a scalar field, it would have been del u phi at null infinity.
Okay.
Something of that sort. Yeah.
So when we are imposing fall-off conditions here,
Yeah, these are u fall-off conditions. Fall-off conditions with small u.
so this is an extra condition,
This is an extra condition.
and it is still consistent with the previous conditions that we
Yes.
R condition.
Yes.
Besides that, like, how do I know I have that freedom?
How do you know you have the freedom of? I don't have a good answer to how you, in general, select fall-off conditions, other than the fact that you want your, say, charges or something to be finite.
So here, for example, here you want this term to go to.
That is one way in which you could have motivated it. Like you want, you want this thing to be a total variation. That is one thing you could have motivated it. The other thing, in general, I do not know if there's a guiding principle which tells you that you have to choose these particular fall-off
These
conditions.
are CK conditions, right? That's what they are called.
These conditions, the NAB fall-off is not the CK condition. You're right that the CK condition is something that tells you that CAB at
Whole formation at scri plus minus or scri minus plus, because it's like the system should revert back to vacuum, and there are no. So it's related to the question that Anirban also asked, like scri plus minus at the future of nullity, you don't get black hole. So you only get the vacuum. You go back to the vacuum. So that's why they impose conditions on the fall-offs of NAV. The CK, this table they found.
Yeah, I'm trying to recollect if CK was that.
That's probably, I think, motivated
I
those fall-offs of NAV.
I think the CK condition, what it tells you is that CAB at some scri plus plus or scri plus minus can be written as DADB of some scalar, something of this sort. I think that's what the CK condition was, but maybe I'm wrong. Maybe I'm.
Yeah, it's like in addition to that also. Like
maybe in addition to this.
Like this form is, especially in this context of flat space, but there they say that your new tensor should follow certain way.
Right. Okay.
And so that you don't get the black hole formation at scri plus minus. So
I see.
That's one of the ways probably to motivate like this fall-off conditions at NAV.
I see. Okay. Maybe, yeah. But yeah, in general, I do not know of a good guiding principle for a general fall-offs.
If you start from the first board on the left-hand side,
Right.
how would you know that you will in future make use of this some freedom in you?
Right. In general, I do not know. Beyond certain usual statements like, you want the energy to be finite or some momentum to be finite and so on.
When you compute those things?
Only when you compute those and so on. In general, I do not know of a good, yeah.
So this continuing with this line question, can you have half integers?
For odd dimensions, you do. For even, I don't think you need half integers. At least in anything, for even dimensions that we work in, you never need half integer fall-offs. But if you're working in 5 dimensions or something, then you do need half integer.
This expansion is also dimension specific.
Which expansion? This expansion, good, thank you. So this expansion in general is valid for any even dimension. But for odd dimensions, you would also need to use half integer fall-offs. You're right. Even dimension, I mean, say 6D flat space time or something.
Could you again repeat the significance of having this to be total variation?
So if once you have it to be a total variation, then basically it means that you don't have this term in here, so you can read what the charge is.
Okay, directly from there.
You can just read what the charge, exactly. So you can compute what QF is. Like in this case, I'll just write down what QF is. Yeah.
And this term vanishes. So yeah, you mentioned that you demand this appropriate fall-off.
Fall-off condition for any B to make it vanish.
So when can you do this?
When you mean I could have I think in this case what would go wrong is if you had chosen a less restrictive fall-off condition than whatever one needs to, then you would have also gotten energy to be energy, whatever you would have defined as conventional energy would also be invalid.
Okay.
Like it would be divergent
So
or something.
very physically motivated.
In this case it can be, but it's just that it's not, there's no step-by-step way to guess what the fall-off condition should be. Like I think Strominger somewhere in his book says that choosing a fall-off condition is an art, not science. But and then he says maybe art is better than science. But okay. But I do not know if there's a step-by-step way to in general guess it. As somebody was saying that it might be related to the CK conditions, and again in this case maybe that's a good motivation. But okay, like yeah, I don't know. Okay, so can I remove this board again, or maybe I can't? Okay. Sorry guys, it's a bit. So I have more, what, 10 minutes or something? How much? 20 minutes, okay. Okay, so if you just follow this procedure and compute what this thing gives you, you'd find that QF reduces to a sum of two terms, something which I'm calling QF soft, something which I'm calling QF hard, where QF soft is okay, in the way I had talked about this derivation, this term would technically be absent, where this TUU matter is basically coming from other kind of fields that you might have, like your scalar fields or something. But had you also talked about a scalar field interacting with gravity, then you could have in general derived some expression of this form. Okay. So firstly, why this distinction between hard and soft piece? So this hard piece is actually perhaps a more familiar piece, because this thing gives you the usual notion of the Hamiltonian. When you've chosen f of omega to be a constant, specifically the lowest spherical harmonic, then this thing is this is the stress tensor of the graviton, and this thing would be the stress tensor of other fields that you have in your theory. Okay? And this charge in here is a generalization of that thing with a function f of omega. The usual Hamiltonian that you talk about does not have the f of omega here, but it has constant of 1 by 4 pi. Okay? So that's one way to think about it. But the way this distinction actually comes about is because of the fact that the hard charge is nonlinear in the news. So NAB, just to remind you, NAB was del U CAB, and this thing is nonlinear in the news, whereas this thing is linear in the news. Okay, so the soft piece is, yeah, that's one more way to just define or distinguish between these two. And one thing that you can specifically notice is that this particular integral, which is appearing the soft charge, roughly goes as just NAB du. There's also the integral over the sphere, but the u integral only affects NAB because f is independent of u. And this guy is like the zero frequency limit of the Fourier transform. Okay? The full charge is conserved. The full QF is what's conserved. That's right. Anyway, so the soft charge has this, just this integral of NAB, which looks like this object, and hence the name infrared is what appears, because this is like the zero frequency limit of the Fourier transform. One can actually show that the Ward identities corresponding to these charges would give you the soft theorems, the so-called the leading soft theorem. Are people familiar with soft theorems, what soft theorems are?
Yes, so you need a single Ward identity for the charge, not for separately. That's why I asked.
Sorry, not for separately as in?
I mean, you would get two Ward identities if they were separately conserved, right?
Two Ward identities. Yeah, but here you just have this single Ward identity. Yeah. But for each value of f, for every f. So f is any arbitrary function on the sphere.
And that gives us the soft theorem.
That would give you the soft theorem. So okay. So what I mean by soft theorems are that if you have some scattering process, and in the scattering process, if you've got one graviton which is soft, then you can relate. Let's say this is having some energy omega. Then the omega tends to 0 limit of this has some universal soft factor. This is only the leading universal soft factor. There's some of the other terms are also soft. Some of the other terms are also universal, but in this case, in this particular thing, you'll only get the leading term. And this amplitude is related to some universal factor times an lower point amplitude. Okay? And you can show that the ward identities corresponding to this charge would actually give you this kind of thing. And hence also, and since there's explicitly an omega tends to 0 limit here, this is also an infrared effect. Okay, any questions about this? F can be any functions on this sphere. Yeah, F can be any function, correct. So there are infinite number of conserved charges. That's right. Okay, I think there was a question before as to how this thing is related to the Gauss constraint. And the way you relate it is as follows. Okay, so remember when I had expanded the metric out, there was this particular component of GUU which looked like m times e power 2 beta plus u squared. And each of these were expanded in large R. In this particular case, the first component of m, which is, so m as a function of u, r, and omega, was written as n equal to 0 to infinity which was minus 1 plus what I'll call mb yeah. Yeah. Oh, no, no, I just wanted to say that the integral of NAB from minus infinity to infinity is like the zero frequency limit of its Fourier transform, or like the zero mode in some sense.
Yeah, but then if you take the limit first, then that factor essentially becomes 1 and you get the left hand side.
Yeah, sure.
Yeah.
All I'm saying, all I wanted to motivate is like it's a zero mode, that's it. It's basically a zero mode of NAB. That's what this integral picks up for you. The right hand side, if you forget about the limit on the right hand side, then it's the it's a Fourier transform of any frequency.
Yeah.
But what it actually picks up is specifically the zero frequency mode.
And because U was like time coordinate.
U was like a time coordinate.
So
Yeah.
omega is like energy.
Correct.
And hence
Roughly
omega
that.
going to-
Roughly. That's right. Yeah.
And is there some like I think this completes one of the things that you the triangle that you.
This actually completes. Yeah, I've not done the derivation, and in fact, it's a long derivation. But yeah, it would tell you the relation between the asymptotic symmetry and the soft theorem.
What about hard? It does not correspond to anything.
No, I mean the full charge is what gets conserved and what enters the ward identity.
Okay.
So the hard piece would give you the energy of the hard external particles. So in this diagram, for example, all these particles are assumed to have hard energy.
I see. So this I plus integral breaks down into u and omega integral and.
Yeah. Oh, so I should maybe thank you. Maybe so I plus is du from minus infinity to infinity and d to omega square root gamma.
So it just takes off that part and that's what you written.
That's all I've written because f is independent of u.
And d is with respect to the gamma.
D is with respect to gamma, the covariant derivative with respect to gamma. That's right.
So when you say that QF is conserved, in what sense are you saying? So it's like when you say some charge is conserved, you usually say that time derivative of it goes to 0.
Yeah,
But
yeah.
you don't mean that here, right?
So here, one way of thinking of the conservation is that whatever QF entered Scri minus should also equal to the QF which exited at Scri plus.
Okay.
Like
So
for
at each point, so this QF at scribe plus minus should be equal to.
QF at Scri plus minus, exactly, which is how you would get the word
That is
identity.
the conservation.
Correct. Right. That's right. Yeah. That's right. Okay, the way you can think about this from the Gauss constraint is that if you specifically look at this component, which is known as the Bondi mass aspect, and the expansion of mu, and if you look at the Einstein equation, the UU component of the Einstein equation, then it actually gives you the U derivative of MB, which has some form like matter. And this full QF can actually be thought of as the value of, it's an integral of MB's value at scribe plus minus. So from this equation, you notice that MB is basically fixed as a function of U up to one integration constant, okay, which is its value at say U equal to minus infinity, right? Therefore, QF actually just looks like this thing, again over scribe plus minus times the, yeah. So this is how your charge is related to the Gauss constraint. Somebody had this question before. You will get the Hamiltonian by choosing f omega to be y00, 0. The 0th spherical harmonic. It's like, I think it's just 1 by 4 pi in this case. So the usual Hamiltonian is obtained by, so for example, if you choose f omega to be a constant, then notice that the soft charge is just 0. Okay, because it's a total derivative on the sphere. And similarly, if you also choose f omega to be just a, I think it's just y10 or something, even then this would vanish. So these are your usual translations. For the usual translations, you would never have seen the soft charge.
You will always be bounded.
Exactly. I mean, it's a boundary term of the sphere, so it's like it just gets cancelled. Yeah.
How do you write limit omega tends to 0 to the power minus I omega?
This relation?
Is it true for any function?
Yeah, all this tells you is that this picks up, I mean, I think it's also commonly known as the 0 mode of NAB. So this integral just picks up the 0 mode. So this, if you forget about this limit omega tends to 0, then this is just the Fourier transform of NAB, right? As a function of omega. Then you take omega tends to 0. So in a sense, all I wanted to motivate was this is an infrared effect. So it's an omega tends to 0 limit. It's an energy tends to 0 limit of something. That's all. There's nothing more than that.
Is your question like, does the limit of the integral commute? Is that the question?
Oh.
Yeah, that is not well understood. I don't.
Yeah. Okay. That, yeah. I don't either. I mean, for any, I think for whatever usual situations people look at it, usually commutes, but I'm not sure of some. Yeah. Mm-hmm.
Here there is no such interpretation.
I don't know of any such relation between. You're talking about this holographic renormalization thing, which the Skenderis-Vanders thingy. I don't know actually. I believe Prahar and others are trying to look at if these can be understood from that perspective, but I do not know if it's been done fully. Yeah. Okay, any other questions? Okay. So I'll mention now why I think once you have got the charge, why I think some part of 4 dimension is slightly more difficult as compared to higher D, and I'll just do this as follows. Symplectic. Oh, sorry guys. Sorry, I wanted to have a part of this board out there. Okay, so like I said, when I wrote down the symplectic form here, and we can discuss this derivation soon, but this basically tells you which variables are conjugate to each other, and it so happened that if you wanted to check whether this charge there generated the supertranslations or not, by that I mean that if you wanted to check if QF and CAB, for example, it gave you back delta F CAB. Once you've got the charge, you could have asked whether this thing worked, whether your charge generated this. And it turns out that if you just use this part of the symplectic structure, that if you just use this commutator, then you end up getting this answer to a factor of 2. So what I think the answer you'd get up would be 1 by 2 of this, and not the exact thing. Okay. So what it actually tells you is that you have to take care of some other conjugate mode in a bit careful manner, or some other Poisson bracket that you initially assumed was 0, you'll have to take it in a bit more careful manner. And those extra Poisson brackets that you have to take care of are basically the values of CAB at I++ and I+-. Okay? So the full phase space then would be parameterized by the bulk CABs and NABs. So these are the bulk values. And along with this, you would have gotten the boundary values of C omega and N omega. These are values at Scri plus, like basically the boundary of Scri plus. Okay, it's actually the difference of the values of CAB at Scri plus minus and Scri plus plus. Okay, so this is something which I think people had to do it by hand, if I understand correctly. Like, it was not an entirely clean derivation as to how this thing came into picture. That why exactly would suddenly, like why should one suddenly worry about the boundary value was not initially clear. So this is, but turns out that once you have taken these into account and you correspondingly add their conjugate modes to the symplectic form, and then you define the modified Poisson brackets, you see that QF indeed generates supertranslations. Okay, but sorry. However, this is something which I feel could have been seen better if you just worked in higher dimensions. Okay, and the main reason is in 4D, what happens is the entire radiative data is actually contained in CAB. Okay, so the CAB, which is dependent on U and omega, this is what captures your full radiative data. By which I mean, let's say your stress tensor and so on. All of these depend on the derivatives of CAB and something. And so it was not clear as to which part of it goes into determining these kind of soft effects and so on. Like for example, even if you look at the soft charge, which was NAB du, it basically is del u CAB from minus infinity to infinity, which talks about the values of CAB at Scri plus minus and Scri plus plus and CAB at Scri plus minus. Okay, and therefore these boundary modes of CAB is actually what enters the soft charge. And so it was initially, I guess, it was not easy to, like, there was some confusion, and then Strominger, Prahar, and I'm forgetting the other authors who proposed that you have to also take care of the boundary contributions to the symplectic form. But this is something which is, I guess, slightly clear in higher dimensions. I'm not going through any of the details. But what so happens is that in this metric expansion that we had, let's see, and so on and so forth. If you're working in some higher dimension, let's say if you're working in 6-dimensional spacetimes, then what you would see is that all the other metric components that you have, okay, let's say UA and so on that I wrote down, can all be expressed in terms of specifically these both, CAB and DAB, where you find that this CAB is what is now, it actually has an equation of motion which tells you del u CAB is equal to 0, and therefore it does not carry information about radiation, or there's no radiation. And the entire radiation is now carried by DAB, or entire radiative information. So the DAB in here, in 6 dimensions, behaves like the CAB in here. Okay? And the CAB in here behaves like the boundary modes of this guy. But you don't actually have to add anything by hand. It's all just clear. And then if you now compute the symplectic structure of this guy, you'd find that you would get DAB conjugated with its del u DAB part plus CAB and some derivatives on DAB. I'm not writing down the sphere derivatives properly, but there's a very clear understanding of how you get the hard and the soft charges in general dimensions without having to add 0 modes of these sorts. Okay, there's just a slight trivia. It's not that important, I guess, but I think if had one looked at higher dimensions before 4D, they would have guessed this, which for some reason they did not. But anyway, so that's just a aside on why I think higher dimensions would have been easier to study. And okay, I think I'll conclude the first part of the lecture now. If I'll take on questions, but yeah.
Can I ask a couple of questions on the high dimension part?
Yeah.
Why does it start with arch there, not after the 4 or something?
Sorry, the metric on this, the usual metric that you have is still this guy, right? du square plus.
You have a 4 sphere, I thought, 6 in 6.
Yes. But it's still minus dt square plus
Okay.
dx square and so on, right? Yeah. Almost everything is the same. It's just that you don't have to take care of these boundary values in some different way. It's all just there in the metric expansion.
So just from structure, if I just identify in this 6D symplectic structure,
Yeah.
CAB with the C0 and the
DAB with this thing, then everything works in the if you're working at the linearized level in 6D, then everything is just fine.
including factors.
Including factors, I don't know. But it so happens that if you consistently follow the derivation of the symplectic form and get to what you should get, then you don't have to worry about 0 modes or something anymore. And one main reason is, the soft charge in 6D actually depends on the integral of DAB, whereas in here it depended on the integral of del u CAB. So therefore, in a sense, soft charge in here was dependent on the boundary values of CAB, but in here it's not exactly boundary value. So in order to adjust for this half factor, what Strominger, Prahar, I think they proposed was that you'll have to take care of the boundary values of CAB in the symplectic form. So once you've written down the symplectic form, what it tells you is what are the non-zero Poisson brackets in the theory. Okay, that's all the symplectic form does for you. And so in this form, you would have just written down non-zero Poisson brackets between CAB at any u and NAB at any u. So you would have gotten the Poisson brackets like CAB u comma omega and NAB at u prime comma omega. Okay, this would be a delta function or something. However, once you've taken, if you find that if you only take care of this guy, like if you only use that Poisson bracket, without worrying about their boundary values, by boundary values I mean boundary of scribe plus itself, then you would end up seeing that you would get a mismatch of the factors. There would be a factor of 2 problem. This integration formally includes what the value of like over all u. It's formally over all u, but you have to find that you have to separately take care of some values at scribe plus. Like you have to separately write down another term in the symplectic form, which is only the boundary value. That's the thing, I'm not sure if it's a very clean derivation or not. It's something that they add by hand. Like they separate the 0 mode or they separate the boundary values and just add it by hand. But
if you separate the boundary value from the past integration,
I'm not sure how to do it consistently. That's the thing. Because once you've been given the values at general u and u prime, then extracting the boundary value from that is a bit non-trivial, which is what they analyze in some detail. They say that, okay, you have to analyze the boundary terms in some detail and then compute the Poisson brackets.
Actually, these things are only all these construction are called IR1 construction. This symplectic form and everything.
Possibly, yeah, I think so. That's right.
There is also a paper by Daniel Harlow. He considered all this boundary term very carefully.
Yeah.
Understand the paper.
Yeah, I know that there's a paper by Harlow, but I do not know what exactly he does in there. Yeah.
Just maybe a couple of comments is that, so once you have the symplectic structure, we don't necessarily have a Poisson bracket because you want the inverse of the symplectic structure.
Correct, indeed. Right.
So what we get, so to do that, what we need to do is, like, for all the Poisson bracket, we need to find the corresponding Hamiltonian vector fields. And you can do that only for the NAB object. So you can write down Poisson bracket for NAB, but you can't write it down for anything that involves AB. So then what you do is let's formally try to integrate the NAB bracket and see that it is CAB NAB, and that runs into trouble. So if you try to use that, you have a factor of 2 mismatch. So what it's telling you is that the phase space that you're getting from the Lagrangian, the degrees of freedom, that is not enough. There are some more degrees of freedom that you're not seeing from the Lagrangian. So you add it by hand and then you get the correct Poisson bracket.
That's right, yeah. In a sense, yeah, just to, thanks for clarifying that, Anisha. In a sense, what happens is, once you've gotten this, if you wanted the symplectic, if you wanted the Poisson bracket between CAB and CAB, then you would have to take care of integration constants. That's another way of saying it. Because CAB is the integral of NAB. And those integration constants are precisely these boundary values of CAB that you have to take into account.
Just from this commutator, could one figure out QF? Suppose one demands that I get QF times commutator CAB. That is your delta of CAB.
I think that's exactly how they figured out these correct coefficients.
Then you wouldn't have to include by hand, right? The boundary.
No, I mean, that's exactly how they figured out the coefficients of these, the boundary terms in the symplectic form. So they assume that QF should generate super translations, okay, and then you add the corresponding terms, like terms which should generate those. Yeah.
What data is this zero mode of CAB?
You can think of it as the soft mode or something. Like,
Can't you just work with it to be zero?
if you work with it to be zero, then you actually are forcing these objects. You see, in this super translated CAB, there's a part of which depends on U, but there's an inhomogeneous piece which is U independent. Okay, so if you started with some CAB which was, say, 0, like some 0 at minus infinity or something, then once you have done a super translation, it would take you to a non-zero value. So it's like, I think if you're setting them to be 0 or something, then it's like you're excluding super translations. You're only working with those functions which are annihilated by this operator, which should be your usual translations. And yeah. Yeah, okay. More questions?
So as I was asking, like in the holography innovation that we do for
Yeah.
ACT, so there are finite contributions to, for example, to the stress tensor, which comes from this regularization.
Okay.
So here you do not have such scheme. So is this story complete?
I do not know if I understand the question.
I mean, so the holography innovation you do, for example, if you come to the stress tensor, it gets contribution from this counter terms that you add or something like that.
Yeah,
It has finite contributions.
Yeah, I don't know. I mean, in this case, all I'm doing is just computing the charge corresponding to some given symmetry. I don't. Yeah, please go on. Yeah.
You can construct a stress tensor like you do for EBS also. That is related to NAB. They have constructed a 2D stress tensor, so that gives rise to subleading soft graviton. So basically, that you can think of corresponding to like ADA-CFT stress tensor. So that is like the stress tensor of the two-dimensional celestial safety they are defining on the sphere. So that stress tensor is related to NAB, this news. So yeah, there's a paper by Strominger there. They have defined this 2D stress tensor for 4D gravity, and that is something that gives rise to soft graviton theorem. So there is such thing, but it's not done using this holographic renormalization. It comes out from a completely different point. But you cannot. I'm not sure if you can see that from the bulk right? This is purely the boundary construction.
Yeah.
And also, since you're not specific about the boundary theory, so why are they exercised in higher dimensions? I mean, it's interesting already.
Well, I mean, okay, the higher dimensions, one way to see is, okay, if you wanted to understand string theory or something, how would all of these generalize to higher dimensions? And then, as I said, my personal interest in this was from understanding how valid the principle of holography of information was, which is what I'll probably talk about in the next lecture. And yeah, and I feel that there are certain things which are just clearer in higher D. For example, you don't have the zero mode tension, which just comes up in 4D. Like,
but I think the zero modes are related to like Goldstone.
Correct.
Right? That's
They're
related
related.
to the spontaneously breaking of
Correct.
BMS symmetries.
Yeah.
So that seems to say like it's naturally coming from that way, right? Because your vacuum is not BMS invariant.
Absolutely, I agree.
Vacuum is
Yeah.
breaking, so then that should correspond to some Goldstone.
Right.
Goldstone modes are C.
I just do not know how it was done chronologically. I'm saying now it's clear, as you said, from various points of time. When it started out, I'm telling this in the way it started out. The way it started out, it was not obvious to guess that you have to add the zero modes, or you have to take care of those in a specific way. Correct. Okay.
Can I just ask a quick question on the higher dimension case?
Yes.
In higher dimension, because you don't have these zero modes, are there no vacuum transitions?
Oh no. So the thing is, what role would have been played by the boundary values of C in here is now played by this CAB. So this CAB now is a function of Z.
I see. But now
It's just a function of Z.
you have like 3 different CABs. CAB is still traceless?
It's still traceless.
You have
Two different CABs. Correct. But the radiative data is contained in DAB, which are 9 in number, which would be the 9 gravitons that you have. Yeah.
So for fourth dimension, there is a half. Now we have to add the boundary term to
Adjust for that.
higher dimension.
You don't have to do any of that. It's all just clear once you write down the, okay, I haven't talked about the derivation of the symplectic form, but if you use the so-called the usual Cherenkov-Witten form and you push it to Scri plus, the symplectic structure that you get naturally takes care of the Goldstone mode, as somebody mentioned. Yeah. Like, you don't have to add any, you don't have to worry about boundary terms and so on. And the main reason is the soft charge, for example, in here is an integral of DAB and not the derivative of DAB. Like in here, it was the integral of the derivative of CAB. That's why it turned into a boundary term. That's why the boundary terms became important. That's right. But in higher D, it's not of that sort. But however, one thing which will be true, and I'll perhaps say it in the next lecture again, is that the full charge is actually a boundary term, because it can be expressed as the metric fluctuation at u equal to minus infinity. The hard plus the soft charge can actually be expressed like this. And this is true in all dimensions, not just 4D. This is the relation to the Gauss law. I'll actually make use of that relation in the next lecture. Yeah, any other questions, comments? Yeah, I can actually share my notes. I'm not sure if they're well written or not, but they have all the, they have these derivations to some partial extent. But yeah, I can share them, sure. Actually, I have only made notes for this part of the lecture. For the next part, I'm going to talk from my paper. But okay, that's fine. I'll still share these. Yeah. Thank you. Sorry, how